Fluid dynamics is essentially the study of the way fluids move, and that includes gases as well as liquids. Now, fluid dynamics distinguishes two main types of fluid motion. One is called laminar flow, and the second one is called turbulent flow. Now, laminar flow is a flow of fluid that consists of very little resistance, and that's because each particle within that fluid follows a smooth specific path, and the paths of two or more fluid particles never actually cross. So if we draw a diagram for laminar flow, we get the following picture. We get the following diagram, where each blue path represents our path of the fluid particle. And notice these paths, also called streamlines, never actually cross. Now, what about turbulent flow? Well, turbulent flow is essentially the opposite of laminar flow, and turbulent flow involves a lot more resistance, and that's because turbulent flow is characterized by erratic small circular currents called eddy currents, also known as eddies, as shown in the following diagram. So these eddies create a lot more resistance than compared to laminar flow, where there is less resistance. Now, let's examine laminar flow much more closely. Let's try to come up with an equation that will help us deal with problems in which fluids are experiencing laminar or streamline flow. So, let's suppose that we have the following pipe. On the left end of the pipe, we have cross-sectional area A1, and on the right side of the pipe, we have cross-sectional area A2. Now, let's assume that inside the pipe, we have a certain fluid that is flowing via laminar flow, so steady streamline flow. Let's also assume that there are no leaks or holes within the pipe, and that means since no fluid leaks out, the flow rate through area A1 and area A2 are exactly the same. So whatever amount of fluid that comes in, that same amount of fluid comes out from the other end. So let's begin by defining what the mass flow rate is. The mass flow rate is simply the amount of mass of the fluid that passes over some time interval. And the equation for mass flow rate is simply change in mass divided by change in time. So let's begin by trying to determine the mass flow rate from the left side of our pipe. So we begin with the left side, this side. And let's label all the terms with 1. So 1 represents the left side, where A1 is the cross-section area of the left side, and the right side is represented by the numeral 2. So let's begin with the mass flow rate through the left side of our pipe. So that means the change in mass of our fluid, change in mass M1 on the left side over the change in time. This is how much mass of fluid flows on the left side over some given amount of time. Now, what exactly is mass? Well, the mass of the fluid is equal to the density of that fluid multiplied by the volume. So, the density on the left side of the pipe, density 1, multiplied by the change in volume V1. And the change in volume is simply equal to the cross-sectional area multiplied by the length that we are considering. So let's suppose we have this much mass of liquid, this much liquid moves this distance over this time interval. So that means our change in volume 1 on the left side becomes our density 1 multiplied by the cross-sectional area on the left side multiplied by the distance our fluid flows, change in L1 divided by our time. Now notice the change in L divided by change in time is our displacement divided by time, and this is simply our velocity. So we see that the mass flow rate on the left side of our pipe is equal to the density of the fluid on the left side multiplied by the cross-sectional area on the left side multiplied by the velocity on the left side. Now, let's follow the same exact procedure for the right side of our pipe. So this is our fluid leaving our pipe via the cross-sectional area A2. So we follow the same exact steps and we get the same exact formula, except now we replace our subscripts with 2. So we see that the mass flow rate of our fluid across the right side of our pipe is equal to the density at that side times the cross-sectional area A2 times the velocity V2. So we get the following important equation. Why? Well, because the flow rates through A1 and A2 are exactly the same. That means the mass flow rate through A1 is the same as the mass flow rate through A2. So we take this and we equate it to this quantity and we get the following result. Now, recall one important fact about liquids. Liquids are very hard to compress. In fact, we can make the assumptions that liquids are incompressible, and that means the density along the left side is the same as the density along the right side, and that means these two densities can be assumed to be constant. And if they are constant, they cross out from both sides, and we get the following simple equation. The product of the cross-sectional area and the velocity of the fluid on the left side of the pipe is equal to the product of the cross-sectional area and the velocity of the fluid on the right side of the pipe. And this is known as the equation of continuity. Now, what exactly is the significance of the equation of continuity? Well, it essentially tells us that if we begin at a pipe with a pipe that has a certain cross-sectional area and a certain velocity, and then we expand the cross-sectional area, well, if we expand the cross-sectional area, the velocity will decrease. And likewise, if we're going the other way, if we go from a large cross-sectional area to a small cross-sectional area, the velocity of the fluid will increase.